Good evening. Today I will be discussing my Lab 5 on Faraday's Law. The purpose of this lab is to conduct a real-life investigation of Faraday's Law using a falling bar magnet and a conducting tube of aluminum foil. Our observations will depend on the physics principles at work here, which include the Biot-Savart law, Newton's second and third laws, Ohm's law, and of course Faraday's law. You will recall that the Biot-Savart law can be used to measure the force exerted on an object by an object with a non-zero velocity, where force is equal to current multiplied by the length of the object times the magnetic field from the moving object. Newton's third law, which states that every force has an equal and opposite reactive force, will be used to find the force exerted on the falling object by the aluminum tube. Newton's second law will be used to derive the position and velocity time-dependent motion functions for the falling bar magnet. Ohm's law, which outputs resistance of a function with change in current and voltage, will be manipulated to solve for the current in the ring. Lastly, Faraday's law will be used to calculate the induced current over a closed path, in this case a ring, by the falling object. The very first step in this lab is to find the north pole of the bar magnet. This can be done easily using a three-step procedure. First, orient your device with the magnetometer app open so that there is no X component of magnetic field. Next, align the magnet on axis with the device. If the Y component of magnetic field is positive, then the magnet is oriented with the north pole closest to the device, since for bar magnets, the magnetic field starts at the north pole and moves in a loop toward the south pole. At this point, you will need to measure the length of your aluminum tube, the width of the aluminum, and the radius of the inner tube. Now, set up your smartphone at a distance so that it is able to record you dropping the magnet. While orienting the bar magnet with the north pole pointed down, drop the magnet into the tube. Use a high-definition video player to find the time difference in when the magnet entered the tube versus when it left. The difference is the time it took for the magnet to fall through the tube. Repeat this process, collecting a total of 5 drop times for the magnet. This is the data I collected. The average drop time was 0.306 seconds. Next, I began the process of coding a model for the experiment. I modeled the aluminum foil as a series of rings stacked along the y-axis. Lines 42 through 48 provide the numerical parameters for the simulation and should not be edited. We used the for loop shown in lines 54 through 46 to create the three-dimensional tube using the ring equations from the previous slide. In lines 72 through 78, I created the bar magnet, modeling it as a cylinder. The mass of the bar magnet was measured to be 0.025 kilograms, and the magnitude of mu for a bar magnet was found to be 2.11 amp-meter squared in Lab 3. In lines 98 through 102, I created a function for outputting the magnetic field of the bar magnet, which will be referred back to many times throughout this lab. In the next section of the code, I created a function for the time derivative of flux through each ring as a result of the moving magnet. Ohm's law states that resistance is equal to the EMF divided by the current. In the case of our experiment, the EMF for one loop is equivalent to the time derivative of magnetic flux. Thus, the current in the ring is equal to d flux divided by resistance. In the last section of code, I created a while loop to stop the graph from continuing to plot points when the bar magnet is no longer in the tube. In lines 175 through 181, I derived a formula for the net force on the bar magnet, which is the sum of the gravitational force and the magnetic force contributions from the tube. Lines 182 and 183 are the kinematic equations used to create the plot of velocity and position versus time. On the left, I have my computational model with the bar magnet represented by the smaller white cylinder and the large gray cylinder representing the aluminum tube. On the right, I have the velocity versus time graph for my code. The experimental average time for the bar magnet to pass through the tube was 0.306 seconds, which is less than the expected time of 0.5 seconds as determined by the code. As the resistivity of the conductor approaches zero, we can expect the magnet to move much slower through the tube. This is because as resistivity decreases, current increases, since resistivity and current are inversely related through Ohm's law. Since the force from the loop on the magnet is proportional to the current, a greater current would lead to a greater force from the loop on the magnet, which would slow the magnet's downward motion. Finally, if holes or slots were cut into the tube, we would expect for resistance to increase as there would be less complete current conducting rings in the tube. Thank you for listening.